This video is on Coulomb's law. I'm Mrs. Estock. Let's get started. Coulomb's law describes the size of the electrostatic force between two charges. Now remember, an electrostatic force is the force of attraction or repulsion between two charged objects. We learned before that like charges repel and opposite charges attract. We can calculate just how big this force of attraction or repulsion is using Coulomb's law, where the electrostatic force is equal to Coulomb's constant, lowercase k, equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. This constant is on the front page of your reference table. K is multiplied in the numerator by your two charges, Q1 and Q2, divided by the distance between them, R squared. If we were to use this equation in a practice problem where we have to calculate the force between a 20 Coulomb charge and a negative 30 Coulomb charge if they are separated by a distance of 2 meters. Well, here we have a positive charge, 20 coulombs, and a negative charge, negative 30 coulombs. We know they'll feel a force of attraction because opposites attract, but how big is that force of attraction? We can calculate it using Coulomb's law. The electrostatic force of attraction is equal to Coulomb's constant, K, multiplied by charge 1 and charge 2, divided by the distance separating them squared. When we plug everything in, K here, remember, is Coulomb's constant, or the electrostatic constant, from the front page of your reference table, 8.99 times 10 to the 9 Newton meters squared per Coulomb squared, times 20 coulombs times 30 coulombs, divided by 2 meters squared. Notice here, I did not include the negative sign with Q2, the 30 Coulomb charge, because here we're just finding the magnitude of that electrostatic force. It wouldn't really indicate the direction of the force, so I'm leaving it out for now. If I plug all this into my calculator correctly, I get a force of 1.35 times 10 to the 12 newtons. Notice we get a pretty big size force here because, number one, the constant is relatively large. 10 to the 9 is a relatively large power of 10. Also, we have two charges that are pretty large as well. 20 coulombs and 30 coulombs is a large amount of charge. So for those reasons, we get a force that's pretty big. To go into a little bit more detail about why I excluded the negative sign from one of the charges in the last practice problem, let's talk a bit more about positive and negatives and plugging into Coulomb's law. Even though charges can be positive or negative, you're just going to insert positive values to the equation because a positive or negative would indicate the force's direction, which it's not really doing here. So we don't want to mislead by saying that the force is in a particular direction by including a positive or negative in the answer. So really just consider including the absolute value of those charges when you plug into Coulomb's law. Now, this equation may look familiar to you because we've done another equation in a previous unit that is a similar format. And the equation I'm talking about refers to the other field force that we've learned about this year. We've learned now about electric fields with electrostatics, but previously we learned about another force that requires no direct physical contact, aka a field force. And that would be the force of gravity. To calculate the strength of a gravitational force, we use Newton's universal law of gravitation, where it's equal to G m1 m2 over r squared. And notice how similar these two equations are. They both have a constant value in the numerator. They're both multiplied by two values in the numerator that are affected by that field. And they're both divided by the distance of separation squared. This is no coincidence. They're both field forces, and for that reason, they both have formulas that are similar in format. Where they're different is that the electric force is much stronger than the gravitational force. If you were to compare the constants, the electrostatic constant K is much bigger than the gravitational constant G. Also, electric forces can attract and repel. Opposites attract and likes repel. But gravitational forces are much weaker, and they can only attract. Masses attract all other masses, but mass cannot repel another mass. So although there are similarities between these two equations, there are some key differences as well. Both equations operate off of the inverse squared law. We've talked about the inverse squared law before with Newton's universal law of gravitation, but to review the inverse squared law for the Coulomb's law equation, if you were to graph distance versus field strength for the electrostatic force, it would look a little something like this. It's the graph of y equals 1 over x squared, where the field strength or the electrostatic force is inversely proportional to the distance of separation squared. This is the inverse squared law. Let's see if we remember the inverse squared law. Also, let's apply that direct relationship with electrostatic force and charge as well. So here we'll get some practice with factors of change. If you want some practice, pause your video and see if you can complete these 5 practice problems on your own. Problem A, if charge 1 is doubled, electrostatic force will also double. That's a direct linear relationship. Question B, if charge 1 is tripled and charge 2 is halved, the electrostatic force will be multiplied by 3 halves. It will be multiplied by 3 and also divided by 2. Again, that's a direct linear relationship with both charges. Question C, if distance r is tripled, electrostatic force will be divided by a factor of 9. So if the distance of separation of the two charges increases by a factor of 3, the force between them will decrease by that factor squared, and 3 squared gives us the 9. If r is divided by 4, electrostatic force will be multiplied by 16. It'll increase by that factor squared. 4 squared gives us 16. Question E, if Q1 is doubled, if charge 1 is doubled, and distance is doubled, the electrostatic force would be divided by 2. It would be multiplied by 2 and also divided by 4, which simplifies to 1/2. So here's the summary of the comparisons between electrostatics and gravity, our two field forces, similar equations for force and also field strength. Notice that the constants, though, are quite different. The electrostatic constant has an order of magnitude of 9, so 9 powers of 10, where the gravitational constant is much weaker with an order of magnitude of -11, showing that gravity is a much weaker force than the electrostatic force. That is it for Coulomb's law. If you have any questions about the equation or how to use it, let me know in class.